So this is the important thing calculated by my model. What I think I'll do next is vary the diameter here and see if there's an optimal currently diameter that would minimize this parasitic heat load to my magnet. So if I plot Q dot C as a function of diameter, you'll see, yeah, sure enough, there's a clear optimal diameter right here at about 0.8, 0.9 centimeters that minimizes the total heat leak, right? And actually, that's kind of an interesting question. Why is that, right? What happens if I have a diameter that's too small or a diameter that's too big, right? What are the competing effects here that are giving me an optimal? And if you think about a diameter that's too big, well, that's kind of interesting. That's a situation where you've made the electrical resistance really small, right? It's a really big, thick conductor. It doesn't have much electrical resistance. It doesn't have much ohmic dissipation. But on the other hand, you've made the thermal resistance really small as well. So you have a really big heat leak from hot to cold, right? If I go out here and make my diameter 4 centimeters, let's make this 4 centimeters, and I run, and I look at my temperature distribution, it's basically linear, right? I mean, that's basically a plain wall. I just have a massive thermal short between the top of my Dewar and my magnet, right? So I want to make that short smaller, which means that's driving into smaller diameters, but obviously I can go too far, right? I go too far and all of a sudden I'm back to having a problem. So if I'm way down here, what's going on? Well, if I'm way down here, I've made my electrical resistance really high, right? So now I squared times electrical resistance is large. I have a ton of ohmic dissipation. This lead is getting super hot, right? So if I go down here and put in, I don't know, let's put in 0.3 or something like that, or 0.2, 0.25, let's try it, right? And I hit solve, and I look at it, my temperature distribution looks like this. I have this really crappy electrical resistor, and I'm trying to dump a ton of current through it, and it's getting really hot, right? So yeah, I'm dumping a lot of energy into the cold end here because I have a massive temperature gradient, right? So some balance of those two things is really what I want, and that's what this plot is telling you, right? All right, so that's how we do this in EASE. I think we'll just maybe start the process of talking about how we would do this using a more formal programming language. Just to be clear, if I go back here to EASE and I start bumping this number of nodes up to 1,000 or 10,000 or 50,000, EASE is going to very quickly say, no, I'm kind of done. I'm not that kind of a program, right? So if you have a very large numerical model, this isn't really going to be your best software to solve it, and you're going to need to be able to solve these big systems using some other kind of software that's more well suited to the problem, right? And this matrix decomposition and Gauss-Seidel iteration, we'll illustrate these in MATLAB just because I'm hoping that you've seen MATLAB before, and it's a programming language that you can use pretty easily. But you should understand that you can use these same techniques in almost any programming language, right? They're very general. So start with matrix decomposition. So let's remember what that means. This is a system of, at this point anyway, linear equations, right? It's just T2 multiplied by a coefficient, T1. So all of my unknowns are linear, right? They're to the first power. So I can put a system of linear equations like this into matrix format, and we just kind of have to remember how we do that. If I have a system of 3 equations in these 3 unknowns, what does that look like in matrix form? Well, each row, right? So I guess just to back up a little bit here, this system of equations is equivalent to this matrix equation, right? I have A, which is my coefficient matrix, multiplied by X, which is my vector of unknowns, and then that equals some vector of constants, right? This equation and this equation are identical. This equation, though, once I get A and B, I can solve easily using any kind of matrix decomposition technique, right? And if you look carefully at what A is, right? If I look at A, each of these entries in A are a coefficient that multiplied my unknowns, right? So this first row in A, this is going to be the coefficients that go along with this first equation. And then which column they go into depends on what unknown they multiply, right? So that's kind of the thing to keep in mind. The row is corresponding to what equation we're talking about. The column is corresponding to what unknown they multiply. So for me to put this system of equations into matrix form is literally just me deciding how am I going to order these unknowns in my vector x, right? So I ordered these unknowns into my vector x here in the logical way, x1, x2, x3. How am I going to order these unknown temperatures into my vector x? And then separately, how am I going to order these equations into my matrix A and B, right? Once I know that, once I've come up with some technique or method for doing that, the rest of it's really, really easy, right? But the first part is actually very important. You have to know in your mind, how am I going to order these unknowns in X, and how am I going to order these equations in A and B? And for this problem, it's so simple that it's obvious. But once you get to two-dimensional problems or any problem of any complexity, that's less obvious, and there's actually multiple ways of doing it. And you need to make sure that you've thought out a way of doing it, and then you're faithful to that way of doing it, or you're going to run into problems pretty quickly. So for this problem, I'm going to do the obvious thing, which is say, if I got to order these unknown temperatures in a vector, I'm just going to put T1 first, T2 all the way to T, I guess this should be, Tn, right? This should be Tn. And then if I got to put these equations into the different rows, well, I'm going to put the equation for T1 in the first row, the equation for T2 in the second row, and then the equation for Tn in the last row. Again, this should be row n. And once I've got that sort of straight in my mind, now it's really just a matter of going back to the system of equation and writing them out so that they look like this system of equations, right? Writing these equations out so that it's easy for me to identify what are the coefficients multiplying each of these unknowns, and then what is the constant that needs to go in B. And once you've done that, you build A, you build B, and you can decompose A and get your solution for X, right? Any software is going to have built-in sort of pre-canned routines that make that very easy, right? People have been thinking about that for a very long time, so they're very good at that, especially sparse equations like this. Okay, so I want to stop here for today, but that's what we'll do next time, is we'll solve these using matrix decomposition. And then the next thing we'll do next time is solve these again, but without putting them in matrix form, instead using Gauss-Seidel iteration. And then the last thing we'll do before we move on, and we'll do this next time as well, is come back and think about what happens if we start to do things that are more interesting, like we make K a function of temperature, or electrical resistivity a function of temperature, or something like that, where these equations are no longer linear, right? How do I modify these different techniques for solving these equations so that they still hold, even when I start to put in some of this flexibility that we talked about up front as being important?